In the previous video on bivariate regression, we discussed some of the theory and foundation concepts for that particular statistical technique. Today we're going to move on and look at one more additional concept and then a couple of examples to show you how to calculate and how to interpret a regression coefficient and your regression models in general. To understand regression analysis, it really helps to understand what's shown in this particular graphic. Here you can see I've got my scatter plot of my dependent variable y against my independent variable x. The points are pretty close around the line. It looks to be a pretty good fit. The relationship is positive and reasonably strong. If you look over on the right side of the graphic, I've highlighted three different points. The first point down low is at the intersection of those two dashed lines. The dashed line, the vertical dashed line, represents some value of x. And the horizontal dashed line represents the mean of y. Now you can see that if we don't know anything about our independent variable, the value of x, then our best estimate of y is the mean of y. And we know that because the sum of the squared deviations around the mean is a minimum. That we learned way early in this particular course. On the other hand, if I have an additional piece of information, say a value of x, and if x is related to or covaries with y, then I should be able to make a better prediction. Maybe not a perfect one, but I should be able to reduce my error. So that second point shown there, the one that falls right on the regression line, is the value of y I would predict if I know that particular value of x. That is, it's y hat conditioned upon a particular value of x. The third point in that graphic that I've highlighted up at the top is the actual observed value. That's the xy coordinate, the point placed at the xy coordinate, and where it actually exists in the data. So we can see a couple of things here. First of all, we know that we can measure the overall error of guessing the mean, or using the mean as my best prediction of that particular case, as the distance between the case and between the mean of y. That is y sub 1 minus y bar. We can also look at the distance between the value I would predict if I know x, that is y hat, and the mean of y. That's how much my prediction gets better knowing x. This is analogous to the between group sum of squares from our analysis of variance. In other words, if I know that the variable x has a particular value, the one I'm using here, that is, it belongs to a group with that value, then I would change my estimate of y by a certain amount. How much? Well, the distance between y hat sub 1 and y bar. In this particular case, while my estimate got better, it's still not perfect. There's still some error there. And that's the part that's left over here, and it's measured by the distance of y sub 1 minus y hat sub 1. It's the unexplained or error or residual part of our model. And similar to analysis of variance, this is equal to the within group sum of squares. I can measure these distances for each point on this graph. I've only broken it down by the one point. The bigger issue to take away from this is that, first of all, we have a total amount of error for each point if we guess the mean. We can take that area, that distance, and break it down into two pieces. That explained by knowing a value of x, in essence group membership, and that part left over or unexplained by knowing x, that's our error or within group sum of squares. Now I don't really care about this particular point. I care about all the points. So I'm going to have to do this operation for every point in the graph. We've mentioned before that the regression line is basically an average. And we know that if we calculate deviations around an average, they sum to 0. So just like our analysis of variance, we're going to have to take these deviations and square them, and then we're going to sum them up over all of our cases. This is going to produce three quantities that go into an ANOVA table. Regression and analysis of variance are mathematically identical, but they allow us to answer questions a little bit differently, and regression analysis is a bit more flexible in my opinion than analysis of variance, particularly when you're using observational data as most sociologists do. So first of all, we have a quantity called the total sum of squares. And you can see that at the top is just the sum of y minus y bar squared. And again, as we saw in ANOVA, this is simply the numerator of our variance that we learned earlier in the course. If we would take that quantity and divide by n minus 1, we'd actually have the variance of our dependent variable. So this is what I would call an unadjusted variance. We're simply not averaging it by its degrees of freedom, or n minus 1. We also have what are called the regression sum of squares, the RSS. Thinking back to our ANOVA lectures, this would be the between group sum of squares. But in the context of regression, we often call it the regression sum of squares. And here you can see it's the sum of y hat sub I minus y bar squared. It's the deviations of the values of the regression line, the predicted values, around the mean, that is the value we would guess if we didn't know x. That's equal to our between group sum of squares. Finally, we have our error sum of squares, and that's given as the sum of y sub I minus y bar squared. So here we're also looking at a variance. We're looking at the variance of how the individual cases, the y sub i's, are distributed around the predicted values. And this is equal to our within group sum of squares from ANOVA. And like ANOVA, these quantities are additive. That is, the total sum of squares is equal to the regression sum of squares plus the error sum of squares. And again, thinking back to ANOVA, we had the total sum of squares is equal to the between group sum of squares plus the within group sum of squares. I mentioned in passing during ANOVA that there's a statistic that we can calculate called eta. And eta is the ratio of the between group sum of squares to the total sum of squares, and it's the proportion of to all the error variation explained by our group membership. The equivalent statistic in regression is called R squared, or the coefficient of determination. And here I'm using the regression context kind of measurements, and I'm showing R squared is equal to RSS divided by TSS. That is to say, the total amount of error I would have for all of my cases if I used the mean as my best predicted value is TSS. If I use y hat as my predicted value, then I end up with a regression sum of squares, or a between group sum of squares, equal to RSS. And therefore the ratio of those two things is the proportion of the variation in the total error explained by or associated with my independent variable. Here's an example of two models to show you how R squared works. In these two models, both the intercept, beta hat sub 0, are equal, and both slopes, beta hat sub 1s, are equal. But you can see that there's a better fit on the graphic on the left compared to the one on the right. And by better fit, I mean the points are more closely placed around that line. The line is closer on average to all the points in the graphic on the left than the one on the right. So while the intercepts and the slope coefficients are identical across these two models, the R squareds are different. The R squared in that tight-fitting model is greater than the R squared in the loose-fitting model. So we tend to use R squared as a measure of the goodness of fit of our model. Now, in a bivariate regression, R squared, shown here, is literally equal to the Pearson's correlation coefficient squared. That's not the case when we have multiple regression models, but that's not the subject of this video. If we take the Pearson's correlation coefficient, which we know ranges from -1 to 1, and square it, then we know that our coefficient of determination has to be between 0 and 1. 0 implies that there's no relationship, or the goodness of fit is very poor, looking at the relationship of our variable x to our variable y. A coefficient of determination of 1, on the other hand, implies perfect predictability. If we know a value of x, we can predict with no error the value of y. And as I've noted other places in the course, you'll never find that in the social sciences unless you've made some kind of error. Let's look at our first example. I've collected some data on different types of crimes, murder rate and the rape rate, for different regions of the country. Normally I'd use more granular data, maybe county level or even state level, but I've collapsed this just to make the graphic a little bit easier to interpret and to make the problem easier to understand. The murder rate is the number of murders per 100,000 people. So it's a standardized rate so that you can compare regions of the country that are more populated to those that are less populated. In essence, we're saying every region has 100,000 people, and for example, in the Northeast, they have a murder rate of 4.1 people per 100,000. In the Mid-Atlantic, the murder rate is 9.6 murders per 100,000, and so forth. Same thing for the rape rate. That's a rate of rape per 100,000 people. I have some descriptive statistics on the left. I always like to look at those to make certain that the things I'm measuring are reasonable and that they fall in ranges that I expect them to. And of course, we can learn something from averages and from standard deviations and minimums and maximums. Down at the bottom, I'm showing the output from Stata of the correlation coefficient. We're seeing a correlation coefficient here between the murder rate and the rape rate of 0.5457. And we can just round that up to 0.55. This is a moderately strong correlation coefficient, and it's positive. So what it's telling me is that for regions that have high murder rates, there's also high rape rates. And for regions that have low murder rates, there are low rape rates on average. Let's go ahead and look at a graphic and see if that helps us understand the relationship. It's pretty much as we saw, as we could infer from the correlation coefficient. I fitted a regression line to this model to kind of help us understand the nature of the relationship, and I've labeled all the points, and we can see that sure enough, as we see the rape rate increase, there's an associated average increase in the murder rate. And again, we shouldn't think of these measures as causal relationships. It's not like rape causes murder or murder causes rape, but just that they co-vary. Areas that tend to have a low rate of crime for one type of crime are low on the other type of crime, and areas that have a high crime rate on one crime tend to have a high crime rate on the other. There are some exceptions. For example, the Northeast tends to be very low in terms of the murder rate and relatively a little bit higher on the rape rate. And the Mid-Atlantic tends to be low on the rape rate but a little high on the murder rate. So they're not dramatically outlying, but they are a little bit different. Let's go ahead and calculate, based on the descriptive statistics from the slide before, our regression coefficient. So if we focus in on this formula, we can see that our regression coefficient, one way of calculating it, is the Pearson's correlation coefficient times the ratio of the standard deviation of y to the standard deviation of x. We know that our correlation coefficient is 0.5457 from the table before, from the slide before, and that our two standard deviations are 2.84 and 7.62. Putting those two things together, we can see that our beta hat sub 1, our regression coefficient, is 0.203. Now, if we look at the table on the upper left, there's a lot of information in this particular table. I'm not going to go through it in great detail at this point. I'll use another example to go through that, another slide to go through this in more detail. But let's just go ahead and focus on a couple of things. First of all, if we look at the coefficient for the rape variable, looking at this model, this tells me that we have regressed the murder rate on the rape rate. And I know that because listed under my coefficient it says rape. My coefficient itself is listed as 0.2032326. And rounding that off, it's the same thing I got calculating it by hand, 0.203. Reading across, you'll see that the next number given is a standard error. That should be a clue that there's a test of significance that we can conduct based on this particular regression coefficient. The null hypothesis is that beta hat sub 1 is equal to 0, and the test of significance, or the alternative hypothesis, is that it's not equal to 0. I typically use a two-tailed test here because my regression coefficient can be negative or positive. It turns out that if we take the ratio of the regression coefficient to its standard error, that is 0.203 divided by 0.1179, we get a t statistic, and that's given in this table. The t statistic here is 1.72, and then I get a p-value for that, which in this case is 0.129. So regardless if I use the t statistic or I use the p-value, I'm going to fail to reject the null hypothesis. The relationship that we're observing in this particular graphic, while it looks to be moderately strong, is not statistically significant. That's not to say that it's not important. One of the things I have working against me in this example is I have a very small sample size. I only have 9 observations. And as you know, anytime we do a test of significance, or typically when we do our test of significance, small sample sizes lead to relatively unreliable estimates, and it's more difficult to reject the null hypothesis. Regardless, I simply don't have enough evidence to reject the null in this example. Now that ANOVA table has a lot of other information. Thinking back to our ANOVA problems, we can see we have a model, residual, and total sum of squares. The model sum of squares is our regression sum of squares, residual is our error sum of squares, and total is obviously the total sum of squares. So we can use that information and we can immediately calculate R squared, or the coefficient of determination. We do that by taking the ratio of the model sum of squares to the total sum of squares, or using the notation I had earlier, the regression sum of squares to the total sum of squares. Looking over on the right, I calculate that statistic and we get 0.2977, pretty close to 0.30. In other words, what we're saying here is that if of all the total variation of the murder rate, approximately 30% of it, or as a proportion 0.3, is associated with or co-varies with or is explained by the rape rate. That's actually a pretty big coefficient of determination, and again, our model's not statistically significant, but I believe that that's due to the small sample size. And if we had done this with state level data or county level data, we would find a strong relationship like this, and one that would also be statistically significant. I've also calculated by hand the t-statistics, one for the intercept and one for the regression coefficient. We're really not too concerned about the intercept in this kind of problem, so let's just look at the one for the regression coefficient, beta hat sub 1. I said before that anytime we calculate this t-statistic, it's the ratio of our slope coefficient to the standard error. Slope coefficient here is 0.2032326, standard error is 0.1179685, and the ratio is 1.72. Now, I haven't given you a formula for the standard error, and for this course, I'm not going to. Just remember, like all of our other statistics, when we calculate our test statistic in step 4 of hypothesis testing, there is a formula for the standard error, and if you ever need to calculate one by hand, you can look it up in any statistical text, and you could do it by hand. Personally, I think we're at a place in the course and a place in your statistical education where you're now ready to move on and use a statistical application like SAS or Stata or SPSS and get a regression output similar to the one I've shown here, and this will be calculated for you automatically. Here's another example of bivariate regression. Here I have 2 variables. The variable labeled safe water is the percentage of a country that has access to potable or safe or clean water. That is water you can drink to sustain life. On the vertical axis, on the y-axis, I have life expectancy, which is life expectancy in years. Each point is a country. You can see here that the relationship is positive and appears to be pretty strong. The points here compared to our crime problem that we just looked at are much more tightly packed around the regression line. So this looks to be a very strong relationship. We have some descriptive statistics down here, and I provide not only the means and the standard deviations, but also the correlation coefficient. We see the correlation between these two measures is about 0.83. So this confirms the visual graphic here that's showing us that this is a very strong relationship, and that we see that as access to potable water increases, we're seeing longer average life expectancy, which is really not too surprising. We can take the information in this table, the 2 standard deviations and the correlation coefficient, and we can calculate beta hat sub 1. And once we've calculated beta hat sub 1, we can use the means in that table in beta hat sub 1 and calculate our intercept. I show these calculations over on the lower right. Again, A real short way, if you have the information handy, if you have the correlation coefficient and the standard deviations of your two variables, is simply to multiply your correlation coefficient by the ratio of the standard deviation of your dependent variable to the standard deviation of your independent variable, which in this case gives us a slope coefficient of approximately 0.2383, or about 0.24. Once we have that information, and if we have the means, we can just plug that information into the formula below and calculate beta hat sub 0, or our intercept. Beta hat sub 0 is equal to y bar minus beta hat sub 1 x bar. And in this case, after we plug in all the numbers, that comes out to be 53.32. Taking now our beta hat sub 0 and beta hat sub 1 and putting it into a model, I get the model at the bottom. Life expectancy is equal to 53.32 years plus 0.2383 times the percentage of a country which has access to potable or safe water, plus an error term. And I've included the error term because this is a statistical function, not a mathematical function. And you can see from the graphic that knowing the percentage of a country with access to potable water allows us to make a better prediction about life expectancy, but not a perfect one. Let's interpret this a little bit. Well, this says that if a country has no potable water, that is, if safe water is equal to 0, that life expectancy is equal to 53.32 years. That's actually absurd, because if you don't have access to safe water, you won't live more than a couple of days. This points to one of the problems with regression analysis, and it's really less a problem but just something you need to be aware of so you don't try to over-interpret your model. If I plug a value of 0 in for safe water, a value that simply doesn't exist in any country in the world, and then I make a prediction about what the life expectancy would be, I'm trying to extrapolate or infer beyond the range of my data. We can see that the minimum percentage of access to safe water is 28%, and the maximum is 100. And the truth is, I'll get my best estimates if I make estimates near the mean, which happens to be approximately 76.1%. I could also say, what if 150% of a country had access to safe water? Of course, there's no such thing as 150%, but there's nothing to prevent me from using some number and plugging it into this model and making a prediction. So I urge you to use some caution when you're trying to interpret your models. Don't try to extrapolate beyond the range of your data. How do we interpret that beta hat sub 0? It's simply an abstract value, typically abstract and not a real value, of y conditional upon x being equal to 0. Now let's look at the slope coefficient. So to understand the slope coefficient, I actually have a little process I go through, and here's how it goes. I always try to interpret this in the most fundamental way. The most literal interpretation of this particular coefficient, this 0.2383, is that for a 1 unit increase in x, there is a 0.2383 unit increase in y. That's a great starting place because it's absolutely correct and it gets you thinking about direction and magnitude. But we can do better than that. We actually know what the units are. So what does it mean to increase x by 1 unit? What we're saying is if we have a country where 60% of the country has access to potable water, what if it had 61% of the country having access to potable water? That's a 1 unit increase. And we can think about the y variable in the same way. We know that beta hat sub 1 is measured in terms of y. Y is life expectancy in years. So 0.2383 is just about a quarter of a year. So now we can go back and interpret this a little more clearly. For an increase in access to potable water of 1% of the population, there's an associated average increase in life expectancy of about a quarter of a year. Now, we tend not to think of things in terms of quarter years. We might be more interested in, well, how much would we have to see an increase in access to potable water to see an average 1 year increase in life expectancy? And it turns out that that's pretty easy to calculate. And all we're doing is transforming our variables a little bit to make them more understandable, to tell a story a bit better. So let's focus in on this little formula in here. We know in general that delta y, or change in y, is equal to beta hat sub 1 delta x. Change in y is equal to beta hat sub 1 change in x. So if I go ahead and solve for x, I get delta x is equal to delta y divided by beta hat sub 1. All I do now is, well, I'm interested in a 1-year change in life expectancy, so I'm going to change delta y to 1. I have my regression coefficient, 0.2383, so I'm going to plug that in, and I get a value of 4.2%. So now we can also add this to our interpretation of this particular regression model. This says to me that if countries are able to increase their access to potable water by 4.2 percentage points, then we could be hopeful that on average we would see an increase in life expectancy of approximately a year. A very powerful story told with numbers. Here's the regression output produced from those data. There's 3 parts to all of these regression tables. There's the ANOVA table in the upper left. We're pretty well acquainted with that. Total sum of squares, residual sum of squares, model sum of squares. If we're talking about literally a one-way ANOVA, total sum of squares, within group sum of squares, and between group sum of squares. We know that we can get an R squared, or a coefficient of determination for this model, which is the model sum of squares divided by the total sum of squares. In this case, 0.6884. In other words, we decrease our prediction error by nearly 69% by knowing what percentage of a country has access to potable water compared to not knowing that. Or nearly 69% of the variation in life expectancy is correlated with or associated with or co-varies with access to potable water. Moving down to the table, we get our coefficients. That underscore CONS is our beta hat sub 0, and safe water is our beta hat sub 1. For each of those 2 rows, we get our coefficient, our slope coefficient, 0.238561, and our constant, 53.32051. We get 2 standard errors, and we know that the relationship is if we take our coefficient and divide by its standard error, we get a t-statistic. And then the next column, we get a p-value. At the end of this, we also get confidence intervals, and we interpret those confidence intervals just the way we do with any kind of confidence interval we've calculated. But let's just focus on the p-value right now. We have a very strong relationship between these 2 variables. 68% of the total variation is explained by our independent variable, and our slope coefficient is statistically significant. So kind of quickly walking through our hypothesis testing steps. Step 1, what's the null and alternative hypothesis? The null hypothesis is that beta hat sub 1 is equal to 0. The alternative hypothesis is that it's not equal to 0. Step 2, what's the appropriate sampling distribution or picture of chance? Well, lucky for us, it's a t-distribution. And I say lucky because we know a lot about the t-distribution and have used it before in the class. Step 3, how much evidence do we need to reject the null hypothesis? For regression problems, you need an alpha value, 0.05, 0.01, or 0.001, and whether you're doing a 1 or 2-tailed test. I'm going to set my alpha value equal to 0.05, 2-tailed. Step 4, go to the real world, collect your data, and calculate some statistic. I thank my statistical application here because it produced this output, so I don't need my calculator and I'm not doing a lot of things by hand. I can see that I get a t-statistic of 9.16 with an associated p-value less than 0.000. Step 5. Make a statistical decision and interpret that decision. In this case, I'm going to reject the null hypothesis and conclude that there's a statistically significant relationship between access to potable water and life expectancy in years. More specifically, not only is this statistically significant, it's positive. That is, as access to water goes up, life expectancy goes up, and then I can talk about my magnitude. Magnitude here says that for every change in percentage, for every 4.2 percentage change in access to potable water, there's an average increase in life expectancy of just about a year. Here's one more example. I like this example for a lot of reasons. The biggest is that it's a negative relationship. Here my two variables are SAT scores and educational spending per student. Now this is by state, so that's average SAT score by state and average amount of money spent on educating students per state. And I find this fascinating that it's a negative relationship, and it points to another issue that we've discussed about in regression. This doesn't mean that there's a causal relationship. If this implied a causal relationship, we would interpret this as saying every time we spend more money on educating students, their SAT scores go down. And that's not true. What's actually going on here is that in states that have low SAT scores, they allocate greater amounts of money to educate their students to try to raise the SAT scores. So again, I'm raising the issue here that in these kinds of observational data, correlation is not the same as causation. In the top right, it provides some descriptive statistics, again, means, standard deviations, and so forth, and the correlation coefficient, which in this case is minus 0.4062. And on the left, we have our graphic. What am I looking for in the graphic? Well, I'm looking to see whether the relationship is approximately linear. It appears to be linear. I'm not seeing kind of big changes or a curve or a bend in the distribution of those points. I'm looking for how closely those points are around the line, and I'm looking for direction. Our correlation coefficient of approximately minus 0.41 tells me that the relationship's negative. As educational spending per student goes up, we see an average decline, an associated average decline in SAT scores. Let's look at the table down below. Our R squared is 0.1650, and that tells me that over 16% of the variation in the total sum of squares is explained by educational spending, or 16% of the variability of SAT scores is associated or correlated with educational spending. That's pretty good, actually. Another way of thinking about it is I reduce my error by over 16% in predicting SAT scores if I know educational spending. But let's get right down to the line about spending and looking at the coefficients. Here we see a coefficient of minus 0.0157547. Now, you've probably figured this out, but if your correlation coefficient is negative, then your slope coefficient also has to be negative. And if your correlation coefficient is positive, then your slope coefficient has to be positive. So we can see here that these both line up, both are negative. And again, this indicates, and going back to our kind of first principles interpretation, for a 1 unit increase in x, there's a decrease in y of approximately 0.0157547. Now we can go ahead and start plugging in the units. What does it mean to have a 1 unit change in x? Well, that's our educational spending per student, and it's in thousands of dollars. So if we were to move from 10 to 11, the implication is that's a 1 unit change, which actually represents $1,000. So let's go ahead and try to say this with all these units put back in there. For every change in for every increase of $1,000 in spending per student, we see an average decrease in SAT scores of approximately 0.016. Now that 0.016 doesn't seem very impressive, and it's a little difficult to interpret. So let's go ahead and plug in some values here. So the next step is to take that information and go ahead and put it back into the original units. And to do that, I really need to look and see how these variables are measured. Now, looking quickly at the means of the variables, I can see that the mean spending is 8,809.137. That tells me that the spending variable is measured in dollars, so that a 1 unit change in x is really a $1 change. So kind of putting this all together, we can look at our slope coefficient and say that every time that for associated increases of $1 in educational spending, there's a decline in SAT scores of approximately 0.016. And that's not a particularly useful metric, but it's technically correct, and you might get away with that in selling your regression model to somebody. But we could go ahead and put this into a metric that's a little bit easier to understand. For example, what if we were to increase spending by $500 per student on average? Well, we would take 500 times our slope coefficient and get a number that's approximately 8, and then be able to put this in our interpretation into a little bit different magnitude. For example, for increases in spending on education of approximately $500 per student, we see an associated average decline in SAT scores of nearly 8 points. Of course, if we'd rather have it in a bigger unit, like say $1,000, then we would know that for every $1,000 increase in educational spending, we see an average decrease in SAT scores of approximately 16 points. What metric you use is really dependent upon the kind of story you're trying to tell and who your audience is. Regression is really quite a great statistical technique, and it's the basis of a lot of different kind of statistical techniques, and if you have a foundational understanding of it, the rest of your statistical education will be a lot easier, since so much of the social sciences depends on linear models based on ordinary least squares regression that are just like this particular example. As usual, if you have any questions, please contact us and ask them. We'll try to get you an answer as soon as possible, and we'll see you in the next class.